Hello everyone, I am Lin Li from Wuhan University of Technology, Wuhan, China. The talk I will present today is about multimodal machine learning. The research directions and applications on deep multimodal machine learning will be introduced in this talk. The outline is listed as below. First, I will briefly explain the characters of multimodal data, then list several core technical challenges in the multimodal tasks. Next, I will introduce some of our workers, and will focus on multimodal fusion approaches and cross-modal retrieval tasks, and summarize this talk in the end. So, what is multimodal data? In general terms, a modality refers to a certain type of information or the representations of format in which information is stored. And multimodal data include multiple such modalities at the same time. For example, a video clip can contain textual, visual, auditory information, while the medium is a means of an instrumentality for storing and communicating information. If we simultaneously use two models of audio information, which makes it is multimodal yet not multimedia, imagine that takes of turning signals or the voice of GPS. Nowadays, multimodal learning has been entering the mainstream of the multimedia analysis and comprehension. The phenomenon of data in multiple modalities coexist previously on the Internet, such as the Fox News articles with textual content, visual videos frames, and auditory voice, posted on the social platform with text and attached images, and reviews on the e-commerce platforms with textual reviews and associated products images. Here, I list several common examples of modalities, such as textual language, visual images, and auditory sounds. The researches on natural language processing and computer vision are developed rapidly in this deep learning time. The embedding for the data in the single modalities is easily accessible through the public available pre-trained models. For the natural language processing pre-trained models, the original continuous back-of-words framework-based word-to-vector model has been upgraded to the transformer architecture-based models. For the pre-trained models on the computer vision domain, the initial AlexNet model with multiple convolutional and pooling layers has been upgraded to the models with more fancy designs with radius blocks. There are some multimodal applications such as speech recognition, event detection, emotion and affect analysis, media description, and multimodal retrieval. The research field of multi-machine learning brings some unique challenges for the computational researchers given the heterogeneity of the data. Next, I will talk about three core technique challenges in the multimodal applications. A single multimodal applications may be confronted with one more than challenges in the meantime. The first fundamental challenge is learning how to represent and summarize multimodal data in a way that explores the complementary and redundancy of multimodalities. The heterogeneity of the multimodal data makes it challenging to construct such representations. For example, language is often symbolic, while audio and video modalities will be presented as singles. Here are two types of representations during the joint embedding learning stage. One is joint representations, which project unimodal representation together into a multimodal space. The other is coordinated representation, which are learned by coordinating the separate representations of each modality through a constraint. The second challenge is alignment. Alignment is to identify the direct relation between sub-elements from two or more different modalities. For example, when we want to align the steps in a recipe to a video show the dishes being made, we categorize multimodal alignment into two types, implicit and explicit. In the explicit alignment, we explicitly interested in finding correspondence between subcomponents of modalities. For example, aligning recipe steps with corresponding instructional video. Implicit alignment is used as a latent intermediate step to better solve a different problem. For example, image retrieval based on text description can include an alignment steps between words and image regions. Based on alignment, simple arithmetic operation can be performed on the learned multimodal representation with good alignment. For example, the representations of an image about blue car minus the textual representations of word blue, and add the textual presentations of red. Whose result can retrieve images representations about red cars. The second challenge is address how to translate the data from one modality to another. Not only is the data heterogeneous, but the relations between modalities is often open-ended or subjective. For example, given an image, we might want to generate a sentence describing it, or given a textual description, generate an image matching it. While the approach to multimodal translation are very broad and often modality-specific, they share a number of unified factors. We categorize them into two types, example-based and model-driven. Example-based models use a dictionary when translating between two modalities. Model-driven models, on the other hand, construct a model that is able to produce a translation. Multimodal translation is a long-studied problem, with early work on speech synthesis, visual speech generation, video description, and cross-modal retrieval. In the next section, I will introduce our work for multimodal task. Now, I will start with the multi-modality fusion approach. Modality fusion is to join information from two or more modalities to perform a prediction. For example, for an audio-visual speech recognition, the visual description of the clip motion with the lip motion is fused with the speech singles to predict spoken words. The fusion approach can be split into three types: early fusion, later fusion, and model-based fusion. Early fusion integrates features immediately after they are extracted, often simply calculating their representations. Later fusion, on the other hand, performs integration after each modality has made a decision, for example, classification or regression. Model-based approach explicitly address fusion in their construction, such as kernel-based approaches, graphic models, and neural networks. For the multi-modality future, we first given examples of user gender prediction in social media data. Without doubt, accurate gender prediction can help a company effectively provide their core user groups with personalized service. However, the problem of information asymmetry generally exists in user-generated content, since users post multimodal content in the social media freely. This can be described in two aspects. The first aspect is semantic complementary between different modalities. For example, a user A, both text and images are not able to present a complete concept. We get nothing more than a message about winning a match ticket, which shows positive sentiment. Similarly, only food match information is acquired from the attached image. By taking both text and image into consideration, it can be inferred that user A watched a football match on the scene. However, it is doubtful intractable to establish a bridge from totally different data modalities. Most existing works simply concrete representations from different modalities or words on the results. These operations establish little communication between text and images, which is insufficient to capture deeper semantics. The second aspect is insufficient information in unilateral modality. Modalities do not always occur in pairs. Image might present less useful information than text with sentimental preference in user profiling. For example, for user C, enough information can be acquired to decide the gender. If someone, just like user B, only sends images, gender cannot be decided. Intuitively, some prior knowledge can be flawed between different data modalities. For example, users who send an image like the user C are more likely to be male. Thus, two prediction models might benefit from each other, especially for the one with poor information. Therefore, we observed that there are deep semantic patterns between text and their attached images. Some available information can be inferred to joint learning and information alignment from higher semantic level. However, the information provided by single model method is sufficient, while most existing method adopts relatively simple operation to derive fusion information, such as calculating, weighting. They cannot well capture the relation between modalities. Multimodal gender prediction heavily focuses on text-image matching relationships. In addition, the semantic understanding of gender, such as sentimental preference, is indispensable as well, which is different from general binary classification task. In this work, we proposed a cooperative gender prediction framework, COPLATE. We use self-attention and sentimental dictionary to enrich the semantic representations of text. And we design a bridge connection component that focuses on the relation of deep semantics between different modalities and balance their information gap. Specifically speaking, in the word encoder, a self-attention layer is introduced to derive a word embedding matrix X for each post. As we all know, self-attention is powerful. It can figure out the relationship without respect to distance. Then, each word embedding is calculated with their sentimental polarity. P is the polarity matrix of the corresponding word in X. One limitation of capturing the relevance between different data modalities lies the information difference. In fact, text information is purer than visual information, which contains other irrelevant information. To balance the information, we developed a bridge connection component. First, consider that the presentation of text and image are embedded in different semantic space. We explore a mapping matrix to project them to a cooperative space, and then their relationship is computed in this space. Since text contains more available information, its representation is employed as a North Star to align relevant images. We can calculate their relevant representations after the information is aligned. Finally, the multimodal regression component. We also consider the fusion of results from different sources, that is, image, text, and their cooperative results. We can also consider the fusion of results from different sources. Then we can derive some extra information since these results are inferred by conducting on different assumptions. We conducted our experiment on the dataset from Pan 2018 competition. 3,000 and 1,900 samples with 1-to-1 male-to-female ratio are divided for training and testing, which follows the competition. For each of them, 100 tweets and 10 images are provided. The state-of-art baselines are from 2 papers. We divided them by whether they are based on future engineering. Although some methods introduce human knowledge to select futures, corporate just show a little weakness. From this figure, our corporate outperforms almost of baselines and achieves the best automatic future learning-based method, which reduced the complexity of a future engineering. Although some methods introduce human knowledge here to select futures, our corporate just show a little weakness. It demonstrates that corporate makes full use of knowledge without much guidance from expert. Some single model prediction results are shown in the table below. Corporate shows an outstanding result when only image is fed into the model. Here, it proves that knowledge is transferred to the image model in the cooperating learning from text. In our experiment, we also studied that the text with sentimental is better than that without sentimental or not. This experiment results show that the text indeed reflects some gender preference information. Therefore, it is reasonable that image shows worse results than text. Here is the result. Compared with the component in the first part of the table, that the corresponding one in the second part, results are all improved into some degree, particularly for the images. The result from the 3 primary classify shows little difference. The observation reveals that the text and the image become complementary knowledge of each other. Through the bridge connection component, A lot of text knowledge is transferred to the image component, and relatively less image knowledge is transferred to the text component. Note that in the second part of the table, the bridge component shows worse accuracy since it is a balanced relation between precision and recall. The second example of multimodality fusion is multimodal machine translation. In the modern social media, people can simultaneously post various kinds of data modalities on different platforms. For most user-generated content, image and text are two typical modalities. Both of them may reflect latent intentions of users, which gives us a feasible approach to boost the performance of conventional text-based machine translation. To this end, in multimodal machine translation, we aim to improve the quality of machine translation by employing image information. For example, we can use black dog and water to enhance the presentation of keywords in the sentence. And the image can also tell the model mentioned bank in the sentence is a river bank rather than a financial bank. However, images generally contain multiple layers of information. For example, the global information reflects the connection between the black dog and water, while the local information can help us recognize the black dog and water and other objects. It is a challenging task to extract useful information from the image and align them to the text to derive a better semantic representation. For most existing methods, most of them generally adopt relatively simple operators to derive fusion information such as calculating and weighting. They ignore the diversity fusion results caused by different levels of image information. We observe that this diversity can produce differentiated knowledge and further generated distinguished translation output. The core idea of our model is to embed a diversity alignment module that align images and text features to improve the representation qualities of multimodal information. Our work uses transformer as the basic network architecture and designs three modules, namely image feature extraction module, diversity alignments module, and multi-perspective ensemble module. Its overall structure is shown in this figure. In most of multimodal works, alignment is defined as the relation and corresponding between subcomponents that found instance from two or more modalities. Attention mechanism allows models to learn alignments between different modalities, such as image and text description. In our work, we use multimodal attention to align text and image features with different levels information and produce different alignments. Consider the different effects of different alignments on translation quality. We further calculate the average probability distribution inferred from submodels that input image and text information to obtain a new distribution table. The word corresponding to the maximum probability value in this table is taken as the output of the word in our model. For example, the multi-perspective ensemble process of the source sentence, a boy stand For example, the multiple perspective ensemble process of a source language sentence, a boy stands with 3 goals, is shown in the figure. The 4 models predict probabilities of the first word are averaged to obtain a new probability distribution table, in which the maximum probability corresponding to in so that the translation of a word in the current time series prediction is EIN. Then re-input EIN into the decoders of the 4 models to get the translation result of the next word in the same way, and repeat this process until the last word is predicted. In our experiment, we conducted our experiment on multi-13K dataset, which extends the FLIC 13K image caption dataset. Each image in this dataset is paired with an English description, and the description is translated to German. Based on transformer, this work reproduces the experiment result of decoder gate, decoder and double attention decoder, and our alignment component as listed in the table. In the table, it can be found compared with the text-only multimodal neural translation model. The multimodal fused with an image is not always better. For example, adding gate structure after encoder or decoder does not improve translation performance, and even the accuracy of the translation model is reduced. For the multimodal translation approach based on the gate structure, experiment results show that adding a gate layer at the end of the decoder at the same time is better than adding one of them separately. The 2 gate structures are filled out some irrelevant information by using image features at the decoder and the decoder stage simultaneously. Therefore, it improves the accuracy of the translation. In our method, a linear layer is added on the decoder side to combine the image feature representation based on collaborative learning. So we get a higher translation performance. Compared with the other models, our approach gains translation improvements by introducing image features of different levels and combine them with attention mechanism to form a diverse alignment. The first table shows that our approach with aligning 2 different levels of multimodal features has generated better translation results than the machine translation models based on text only. In our approach, K always include the image features in attention mechanism. Text features. K is not equals to V means that we only include encoder output. When K is equal to V means that we include the image feature and the text feature at the same time. Compared with the result of 2 and 3, our model's performance in 2-dimension local image feature is better than that of using 1-dimension global features. Because 2-dimension local image features extracted based on different channels can express deeper semantic information. Therefore, it increases the effect of image features in the model prediction stage. Compared with the experiment of 4 and 5, our models with 2-dimension local image features does not always have advantage. I will introduce 2 solutions to the cross-modal retrieval task on recipes and food images. As the internet grows, so does the difficulties and complexities of traditional tasks, which are upgraded from unimodal tasks to multimodal tasks. For example, the traditional text retrieval or image retrieval tasks has upgraded to the cross-modal image to text or image to video retrieval tasks. And the task of matching Machine reading comprehensions or Q question and answer based on text has been upgraded to visual question answering task, where a textual question is needed to be answered based on a visual image. Due to the semantic gap and the modality gap between different modalities, in order to copy with cross-modal machine learning task, we need to address the three problems. First, how to learn representations for input data from different modalities. Second, how to copy with the interaction between different modalities. And third, how to design a training strategies for different modalities. In our works, we focus on incorporating external knowledges and multiple semantics to level the gap between the heterogeneous modalities. This is our cases for food image and recipe cross-modal retrieval. Since people are increasing concerned about healthy diets and nutritionally balanced menu these days, millions of food recipes and food images are available on social medias. Food computing has become an attractive research field. One of the most relevant tasks is cross-modal recipe retrieval, whose goal is to find a relevant cooking recipes giving a good image and worthwhile. Several challenges exist in this cross-modal recipe retrieval, which are how to effectively encode recipe and titles, instructions and ingredients, and how to deal with lots of noise in the food images, and how to enhance alignment between two different modalities. In the first solution, we propose a sentence-based noisy-based joint learning framework as shown in this figure. ResNet and BERT encode food recipes and images respectively. Three attention networks are applied to handle title, ingredients, and instruction embeddings. Because there are a lot of noises in the images, food images are filled by recipe embeddings. An adversarial loss is used to enhance modality alignment, and the triple loss is improved to reduce the effects of noises. For a recipe, we have a recipe title here. Instruction and ingredients. They are encoded by BERT separately, and the output of the embeddings all include multi-layer sentence layer information, with surface features in the low layers, syntactic features in the middle layers, and sentimental features in the high layers. We use three attention networks to process these three embeddings respectively. We aim to reduce the effects of mismatch image recipe pairs and useless noise information in the food images. So we applied attention network with recipe to extract effective information from images. An adversarial loss is used to enforce the distribution alignment between modalities. During the optimization, the discriminator tries to distinguish recipe embedding and field image embedding, but we aim to align the distributions of image and recipe modalities and made the discriminator fields. In the last stage of the training framework, we found that a lot of alloys are very close to the anchor point when we use the triple loss with hard example mining. We can draw a cycle that its radius is the distance of the furthest positive recipe to the food image anchor point. In short, we round the radius of the cycle to be small enough that there are few negative recipes in it. The embedding of all images for a given recipe should be close to this recipe. At the same time, distant from other recipes in the common latent space. The experiments are conducted on the recipe 1 million dataset. Following the previous works, the dataset is split to training and testing and validation data. Median rank population of true positives for all the queries and the fraction of times are true positives are ranked among the top K results are selected as our evaluation metrics. We example 10 different subsets of 1,000 pairs and 10 different subsets of 10,000 pairs from the test. We just follow the previous work. Here are the benchmark baselines used in this work. CCA aims at maximizing the correlation between similar pairs. SAN learns a joint space by boosting the similarities between images and their corresponding recipes with a two-layer attention mechanism. GNE uses a pairwise cosine loss to find a joint embedding between image and receipt modalities. ATTEN apply attention mechanisms to receipt titles, receipt instructions, and ingredients. ADAMINE use a double-triple loss and adaptive learning schema. R2GAN is built on cross-modal embedding and generative adversarial networks. ACME is a state-of-art for food image retrieval. We show the performance of our framework against the baseline in this table. In the retrieval tasks on both 1 key and 10 key test dataset, our framework outperforms all the baselines across all the metrics. We can observe that multi-layer sentence attention network component and image field component can extract sentence level information and field noise information in the images. We show some examples in these slides. 3 different kinds of recipes are input, stew, cake, and roasted recipe into our framework. As we can see that the top 5 images can capture semantic information well between 2 modalities. For the second recipe about the roasted broccoli flour, the fourth and the fifth images are fried chicken and fried lamb chops. We think that the main reason for this result is that our framework does not give enough weight to the food categories in the recipe title. And this figure shows that image to recipe retrieval result. The image queries with complex background are chosen from recipe 1 million. We want to test our image filter component with this image. As you can see that the image filtering components works well in our framework. Even the top results are very similar. Our framework can retrieve right one. Next, I will introduce the second solution to the cross-modal recipe retrieval task. To start with, we look at the corresponding common latent space figures of ACME, a state-of-art work on this dataset, and our work SEJE. Connecting the same recipe query. The matched image denoted as the red cross, red cross, is far away from the recipe query, denoted as the centric red square here in the ACME result, which indicates that ACME does not map the recipe and the food image to the common space properly. As the right figure for our SEJE approach, the matched images is very close to the recipe query embedding, since SEJE incorporated multiple semantics in the joint embedding learning. That is why our SEJE can get better results. To issue the efficient learning of the 2 embedding functions, we introduce 2-phase deep future framework for sentimental enhanced joint learning. We call it SEJE, which is performed by leveraging additional semantics in both pre-trained fields, field 1, and the joint embedding fields, field 2. Now, start with the phase 1. In the pre-training, 3 semantic features are from the raw data is added into our framework, which are key entity semantics from the recept text, recept sequence semantics, and external semantics from the image. Here is the overview of phase 2, deep future engineering in our pre-train for task. The weighted entity features and the sequence of sentence features are extracted in this phase. The details will introduce respectively in the following. The recept entity semantics is utilized to capture the levels of discrimination significantly contributed by each entity to its recept text. The inherent problem of most existing work is that they learn every entity in a recept similarly, overlooking the fact that the discriminative significance contributed by each entity is different. The recept entity semantics are obtained by pre-trained recept semantics encoded with 3 main components: entity extraction module, entity reading module, and entity embedding module. In the entity extraction module, key entities are broadly divided into ingredients, cooking, and actions. In order to extract ingredients, built LSTM networks are trained to identify the word sequence that are ingredients with high probability. Then, logistic regression is performed on the extracted word sequence to determine if the extracted word sequence is an integrated entity or not. Look at the example here. The ground beef is successfully extracted from the ingredient text, so it is labeled as true, but the red kidney bean fails to be identified and labeled as false. These with true labels are regarded as integrated entities. Instead of removing this word sequence label as false in the existing word, we connect all the true integrated entities in the whole dataset and re-examine every false labeled word sequence if there is any true integrated entity. If yes, we will also extract these integrated entities from the first word sequence to make sure that we do not miss any true integrated entity. In this way, the red kidney beans can be recovered in this case. As for the cooking and action, part of the speech tag approach is utilized to extract nouns and verbs in the pre-processed recept text without ingredients. After getting the entity from the entity extraction module, we need to identify the entities that are distinguished its recept from other recept. We can achieve this purpose by using an entity rating algorithm such as TF-IDF, text rank, BERT-based approach. To get entity embedding for each extracted key entity, a word 2-vector model is trained over the recept text in the training data based on the word 2-vector framework. Each key entity can get its entity embedding through the learned word embedding matrix. Combine the entity embedding weighted by their significant weights, the recept entity semantics features are obtained. As for the recept sequence semantics, considering the cooking instruction are quite lengthy, using a single STM to obtain the overall instruction embedding may suffer from the distinguished gradients over so many time steps. Therefore, we obtain this word sequence level semantic levels of each instruction by a pre-trained LSTM-based instruction sentence encoder, whose output is fed into the next recipe embedding learning process. For the image side, since food image is a highly condensed form as output of the following the recipe instruction, external semantics need to be incorporated into enriched image information. So the image category semantics from the food images are incorporated in this work to enhance the alignment between the matched recipe text and the food image embedding. In our phase 2 deep future engineering, we'll train a joint embedding model by leveraging the output of the phase 1. The recipe text embedding, the image embedding, and the joint embedding loss optimization will learn concurrently in the joint embedding model. To efficiently optimize the learning of joint embedding loss, we design three primary loss function by the batch hard triple loss empowered by the a lower double lective sampling strategy, and further enhanced by incorporate two external loss function, that is category-based alignment loss, and on both cooking recipe and food image, and the discriminator-based alignment loss. The triple loss optimization is to ensure that the positive instant in one modality should be close to the anchor point in the other modality, and the lective instant instant should be distinguished from the anchor point. So in our work, we optimize the batch hard triple loss by introduce the double lective sampling. So giving an anchor point of one modality, its other modality as the positive instant among the remaining lective instance in the match, we select the hardest lective instance using two constraints closest to the anchor point in the joint embedding space, but with different category label. So the category-based loss optimization on both learned recipe and image embedding is one of the external loss function, which aims to reduce the cross-entropy loss between each modality-specific embedding and corresponding categories, improve the category distribution alignment between the textual recipes and visual images. The second is our discriminator-based alignment loss. Is the other external loss function, which utilizes the competing strategy like those in game with the gradient penalty. Similar to the alignment loss in the case 1, we train a discriminator model such that given a embedding from one modality, this discriminator can tell whether it is from the image or recipe text, which is against the goal of a good quality of joint embedding learning. If the trained discriminator cannot accurately discriminate the source of the embedding, it indicates that our joint embedding learning is effective and the learned joint distribution for matched recipe and image pairs are too close in the joint latent space so that the discriminator cannot tell them apart. Then we combine the three loss together. This table shows that performance our SEJE approach for image to recipe and recipe to image retrieval against the baselines. We observe that our SEJE consistently outperforms of all baselines on 1,000 and 10,000 testing tests, shows that the effectiveness of using the deep future engineering techniques to incorporate additional semantics for further optimizing the cross-modal joint embedding learning. We also evaluate of different entity rating algorithms used in the entity rating models, TF-IDF, text rank, and 3 popular BERT models, which are standard BERT, distilled BERT, and robot BERT, which indicates that selecting the TF-IDF approach in the entity rating model can yield the best accuracy in this work. This figure provides visualization result of the image to recipe query, which shows that the ground truth recipes and the top retrieved recipes based on 6 different images query. We consider 2 recipe categories, cheesecake and pad thai, and in each category, cheesecake and pad thai, and in each category we list 3 image queries. It shows that almost all the significant ingredients of the true recipe and visual components in the image query also appears in the top retrieved recipes. This figure visualizes the result of retrieving a top 5 images using 3 different recipe queries. In all cases, most of the retrieved images share the same similar ingredients to the ground truth images and contains the visual components. For example, in the first examples, all the retrieved images contain the visual components of the stuffed chicken, right, as suggested in the category labels. This figure shows the distributions of the land recipe and image embeddings by our JESE. And we compared with ACME and JESR, right? Based on the TSNE visualization or 1,000 randomly selected recipe image pairs from the test set, we can find that the distributions of recipe and images embedding land by JESR vary greatly, which accounts for the low accuracy result in the cross-model retrieval task. The distributions land by ACME are much better, but still not very similar. Our SEJE approach aligns the distributions of land recipe and image embeddings well, and their distribution and visually similar. To investigate the robustness of our JESE against the largest dataset beyond 10,000, we further compare its MEDR performance against the state-of-art approach, ACME. It shows that the result for image to recipe retrieval and recipe to image retrieval, the gap between our SEJE and ACME larger as the testing set size increase. One of the important measures for cross-model embedding is measure the capabilities of their land representations using simple arithmetic operation. This figure shows that the visual result of arithmetic operations here on the land embedding by our SEJE model, specifically giving a recipe of an apple muffin. We can transform the land embedding of apple muffin into an apple pie by subtract and adding the mean recipe embeddings of muffin and pie respectively. This semantic vector arithmetic result indicates that the recipe and the image embedding aligned in our SEJE model are semantically well aligned, which facilitates that the further works of applications in recipe ingredients analysis and cross-model generation. Okay, in summary, a taxonomy of multimodal machine learning is introduced, which exists 3 core technical challenges: translation, fusion, and representation learning. A more recent interest in representation and translation have led to a large number of new multimodal algorithms and exciting the multimodal applications. That's all for today's talk. Thanks for listening. If you have any questions, you can email to my mail address.